Hello, I'm very glad to see you. Today our talk will be Scale Out and Conquer, Architectural Decisions Behind Distributed in-Memory Systems. Just a few words about me. My name is Yakov Zhdanov. I work for GridGain. I am Apache Ignite committer and PMC member. I have passion of making my product better and better, and I live in St. Petersburg, Russia, so I think everyone noticed this terrible Russian accent. By the way, there will be no Q&A session because I learned this presentation by heart. So what I like about my job, not in particular in GridGain, but about the whole IT sphere, is that we are lucky to have things changing very, very quickly. Every day we have some new trends, some new technologies come out, and now one of the most interesting and very promising direction is in-memory computing. So in memory, when we're storing data in memory, that's probably the fastest place to access our data. So, and memory gets cheaper, and so this opens a lot more interesting things. But what I want to say is that why very often it is not it's not enough just to install, let's say, Apache Ignite and load your data to memory. So from time to time I see that users cannot achieve good performance, good numbers, just because they somehow messing the distributed system with a classical monolithic system. And to get the max out of the distributed systems, you need to have some architectural background on how this system actually works, and what are the mechanisms, and how can you get the maximum of the system when you use it. Okay, here will be our plan. So first of all, we will talk about data, affinity, and affinity function examples. So we will, I will have some examples on data partitioning and collocation. This is our second point. The third point, we'll talk about the synchronization in distributed systems. And the fourth, the last one, is the multi-threading, the architecture of local multi-threading. So I will show some real-life Apache Ignite examples. Okay, so let's start with data partitioning and affinity function examples. When I do some cache operation, for this example, it will be just a simple put operation. I need to think, I need to decide on what, on which node data resides for that particular key. Actually, to take decision against each key is not so much convenient. So in systems like Apache Ignite, we operate with partitions. So the whole key set is split into the partitions, and then each partition is mapped to node. So you can think about it in this way. So when I do put, I first of all map, I calculate which key, which partition this key belongs to, and then I go to the node where the partition resides. So for me, this is a pretty simple operation, and then I can come to that node and do whatever I want with my data. So distributed systems, they are very interesting from standpoint of the scalability. So if I have, let's say, two nodes, and for now I have like 15 TPS per each node, when I add the third one, my data spreads evenly, and I have 33 TPS per each server. I mean, this is like a kind of example, but example affinity function, which is pretty naive, and this all the partitions are mapped to nodes with a simple mod operation. So this gives me the even distribution. So each of my nodes has only 4 partitions, which is probably not too much real life, but still. So when I have 2 nodes and I have some mapping, partition to node mapping, when I add the third one, my data gets rebalanced, and you can see this picture. But so let's take a closer look. So when the new third node comes, we have some partitions moving to the third node. This is fine, and this is exactly what we wanted to achieve. But there is also some kind of parasite traffic, which involves nodes that already were in topology when the third node came. So this is a problem of, let's say, mod function, for example, and the problem is that partition to node mapping depends on nodes count. That should be somehow fixed, and there is several algorithms that allows us to do so. So the first one is consistent hashing, and the second one is rendezvous hashing, or highest random weight. So you can read on Wikipedia about them, and standard Ignite affinity function is implemented over the rendezvous hashing algorithm. So in a brief, you can assign some weight for a pair for partition and node. And the node with the highest weight for that partition wins, and partition gets mapped to that node. So imagine I have node 1, and weight for some partition on this node is 100. When second node comes, and weight for that partition and that node is 50, so this partition does not move anywhere. It stays on node 1. But when third node comes and have a greater weight, then partition will be moved from node 1 to node 3. This is how it works, and this allows us to eliminate the parasite traffic. So here we have only good ones, which loads data to the new node, and we have absolutely zero traffic between nodes who already were in topology. The drawback of this algorithm is that they will hardly give you even mapping. Sometime they will be not even, but for large number of partitions, large number of nodes, this effect will be less visible. But this is what you need to account. This is what almost every distributed system works this way. So you need to know how data is distributed along your grid, how much memory you have left on that node. This is very important and good to consider. Okay, data affinity collocation, what is this? So imagine we have a class customer which has 2 fields, the ID and the city the customer lives in. Imagine I need to update 2 user accounts, and I want to issue 2 update commands. This can be like SQL update or update through cache API, doesn't matter. But the point is that I will need to go to 2 different servers. So ID1 got to some partition which resides on node 1, and ID2 got to that partition which resides on node 2. Let's count the messages we will need to send over our cluster. So we have 2 nodes, so we need 2 messages. So if we have backups, we also need to send messages. Primary nodes should send messages to backups to make the backup copy up to date. Since we use 2-phase commit protocol, the message count doubles for us, and every arrow is not just single message, is a pair of a request and response. And therefore, we have 16 messages. And we have network between each of our nodes, which is really slow compared to the local operations. So how can we affect the situation? How to make things better? We can apply such a technique, which is called affinity collocation. So this is Apache Ignite API. I can simply put an annotation affinity key mapped to the key field. And this will mean that customers having same city will be staying on the same node, technically in one partition. So for now, my two updates will go to one node instead of two. If we do the same arithmetics here, so we will see that we have one node, we have one backup, everything gets very simple. In case if transaction has only one primary node, this way we can fall back to one phase commit. And then we have request and response, and we have only 4 messages. So 4 messages instead of 16. I didn't change anything like in code. Code's still the same, so it's 2 sequential updates. But in the first case, it was 16 messages. In the second, it's 4 messages. So that's why sometimes distributed system not bring you some performance benefits. So probably this is one of the reasons why it is so. So let's we need to analyze and do some analysis just to find out all places of the kind and to fix them. So you see, code has not been changed. We changed only data mapping, which technically dramatically changed the situation with the update and all other operations. So okay, let's query our data. In distributed systems, in general case, query, when I wanted to issue an SQL select, I need to broadcast it. Once I don't know the special case, let's say when in where clause I have the primary ID, so then I'll go to that particular node. But in general case, all SQL queries in distributed systems, they are, probably will be broadcasted to all the nodes. So let's see what's happening in this way. So when I have one node and I need to do a full scan query, and if I add 3 nodes, two nodes to the cluster and have 3 nodes, I will have latency, 3 times better latency and 3 times more capacity in the system. So in this simple example, yes, this adding a new node helps my queries to run faster and reduce latency for my queries that needs to scan a large amount of data. Okay, everyone knows that if I apply index to my data, then my queries can run faster. Okay, let's try it. So if I have one node, I have one big index, so for local data set. If I have a cluster of n nodes, then I have some kind of a forest of indexes. Each of the local indexes on the local data that reside on that node. Okay, let's do some simple arithmetics. So index is in general case, is a binary tree, so we search within, let's say, 1 million of entries. We need to do 20 comparisons at most. Okay, if I share this million into 3 nodes, then I'll have like 300,000 per each node, and it will be only 18 comparisons. So you see that having indexed data, in this case, so adding node, the idea is adding new nodes, in this case, will not help to improve anything. So you'll probably see that system stays the same. We have same latency and same capacity. But if we do index and collocation, so we do the same trick as we did several slides before. So we put all the users living in one city to one partition. This way, I will have same latency, but 3 times more capacity. So my system will be capable to process 3 times more queries with the same latency. So this how this should work in this case. So same, if I apply index, I would probably think about collocation if the queries for that index are common use case for my system. Okay, let's talk a little bit about distribution of data with collocation. So MSK is an abbreviation. This is Moscow, the largest city, the capital and largest city in Russia. St. Petersburg is second largest city, but is probably twice less than Moscow. So if we do this way and we collocate all the data, then we will have some partitions very big and some partitions pretty much smaller. So in order to fix this, we need to probably think about splitting Moscow into several partitions is one of the solutions. Another solution is to maintain the equal data amount on each node. So I can combine larger partitions with smaller partitions. So I need to always play with it. I need to know what my system is doing and when and where my data goes to. So just beware of that. That use of collocation may kill some of your nodes with out of memory, but if you know that this may happen, you will be ready to fix this situation before any critical event comes out. Okay. Joins in distributed environments. So imagine we cannot apply data collocation for some reason. Let's say customer has already been collocated by another attribute. So in this case, we will need to have such a thing which is called distributed joins. So I will go in order to complete this join, as join SQL query, I need to select customers and then to select city on whichever of the servers my city resides. So what can be done in this case? So first of all, what can be done to avoid these distributed joins, because they are really very complex in terms of they are involving many network communications. Therefore, they are slower, much slower than local joins. So how can I switch to local joins in this situation? Very simple solution is to put city to a replicated cache, which means that the whole data set will be replicated on all the nodes. If my city table is pretty small, then I will not have any problem by switching to replicated cache for that particular case. Okay, any questions so far? Okay, so let's go and talk about synchronization in distributed systems. If it was not, I'm sorry. Let's do it in a Q&A, okay? After the talk. I mean, the questions regarding the slides or something like that, okay? Just 1 minute. Okay, or 1 second. 1 second question. Okay, so imagine we have a requirement to implement the local counter. So I'm assuming everyone knows how to program Java. So in this case, every developer will probably take this just atomic long counter, and whenever we need the next value for that counter, we just call counter increment and get. For some reason, we can say, no, there will be a lot of contention and blah, blah, blah. So we need to speed things up. But personally, this code is put here just for example. I'm not sure if there is a really need to do in this way in case you are not writing some ultra low latency application. But still, this reduces contention by acquiring some interval, which is 100 or 1000 in this listing, and then all that counters between the within the resolved interval, they are given without accessing some shared memory, without synchronization overhead. So yes, in some synthetic benchmarks, this code will show a lot better performance than the first one. But here we have the processor with its registries, which are extremely fast. But in a distributed system, we have a wire, which is very, very slow compared to the speed of processor. So if we measure the throughput of local implementation, we will see that it can give millions of operations per second. Distributed implementation, in turn, will hardly giving like 1000 operations per second. So for now, let's discuss the following. So I want to show you how we can simplify our task and get additional performance benefits only by manipulating with the requirements. So, okay, so we need to do counter in distributed systems. So what we can do to have unique, monotonously growing 8 bytes counter. So the first idea is to have some server which will increment this counter by each client request. So this is like, here we satisfy all the requirements. Our counter is unique, it's monotonously growing, and it is of 8 bytes long. Okay, so but this really is very hard to support this counter, because every time client needs a new value, it sends a network request and waits for the response from the server. In this scenario, we remove the requirement for monotonous growing and implement the same approach as I showed you in the listing before. So each client reserves some interval, and all these IDs in that interval are given locally without going to server. This way we save a lot of network calls, and we just don't need to do them, because all the counters and all the information I need to get to give the next counter I have locally. I go to the server only if my interval has finished. This way I need to go to the server and reserve a new interval for me, for this particular client. Okay, but if we remove the requirement that our counter should be 8 bytes and monotonous, I can and it should be only unique, then I would say that Java with util UUID random will work perfectly in this case and will be a lot faster than any network call, despite of the fact they use secure random inside. By the way, we also have some utility class in Apache Ignite which works in the same way. So synchronization, you can think about synchronization as a friction for a car. So, bless you. So we definitely need synchronization just for application to do its work, because it will not be, then be possible to just write even a simple application. But we should not add too much synchronization, because it will interfere with the application and it will mess and will not allow us to achieve the optimal performance. Okay? So another point is that if we, how should we process our data? Should we move code to data or data to code? Let's consider the following example. So here I have a logic that gets an account from a cache, adds some amount to that account, and put them back. So here I have two network calls. First of all, I need the current value for that account. This one is the first network call, and the second network call is this call which saves the account back to cache. So this operation particular can be changed with the following approach. I can replace this sequential get and put by an entry processor which will be sent to that particular node and executed on that side. So this example shows us that I can reduce the number of network calls simply by using the proper API. So the code, the application logic remain the same. I still have an account, I still add 100 to it, but I do only one network call instead of two. What if we have a bug? Then the question that comes out very often. So yes, in this case, when we have, when we have code and data separated, then we just remove the node which contains the failure logic and replace it with a proper one. In this case, when our code is deployed to where data is, we need to restart the whole server, which means that this will involve rebalancing and some side effects we need to be aware about. But in any case, write more tests and try to fix all the issues before they got deployed to production. Okay. Now a few words about local multi-threading architecture. So Ignite utilizes concurrency very heavily, so it starts many worker threads inside, but the model is pretty common. What I want to show you is that we have workers that are accessing some keys in our cache. As shown on the picture. Imagine we have several workers accessing the same partition at the same time. So this produces some contention and workers interfering with each other, and they cannot do the whole work. They could do better if they will be split. But okay, another picture shows that Ignite does not in general case, Ignite does not produce the tasks locally. It gets them from the network. Then the network workers submit the requests to the queue, and then workers pick them up and process that queue. Imagine we have like 3 get or put requests, which goes to the same partition, and they were picked up by these workers, and then all this resulting into several hotspots, which are obviously the queue to submit the request to worker. And another hot point is the actually the data workers need to access to fulfill the requests came by the network. This is like some kind of a bottleneck here, and we. So what could be done here? So we simply switched to thread per partition model, and where each worker accesses only dedicated piece of data, so workers are not interfering with each other. And as far as queue, we split them and have the personal queue per each worker, which of course scales much better on larger systems having several CPUs on board. But so you need still to be aware of the situation when you have thread per partition. So you know that, yes, this system works in thread per partition model. So if I scan, let's say, the data set, some of the scan queries will be very fast, but some will be a little bit slower, just because we have this effect when we collocate the data. Some partition can grow, and others can stay pretty small compared to the largest one. So we just need to be aware of that, and probably revisit the processing for that particular queries and do it in some other way, probably. Because thread per partition model helps very much with the simple use cases, with low latency use cases, with just simple get or put requests, but it can make things a little bit more complicated when it comes to a little bit more complex process. Okay, so coming to the conclusion, let's go back a little bit and see what we have learned during this talk. So when we're dealing with distributed systems, then we definitely have some then we definitely have some approaches and some facility to affect data distribution and data collocation. We need to achieve balance and stability, and be aware that we not just loading data to the distributed systems, but we should know exactly how it is distributed over our cluster, and are there any problems with the data partitioning. So another good technique I showed you is collocation. So collocation can speed up update procedures because I can decrease the number of nodes involved into the update operations which I showed you, and it can also help with SQL queries. Another point is that data model should be adopted accordingly. So we cannot just take the schema from Oracle or MS SQL, let's say, and just put it to cache. This is like an ideal system we are going to, but we are still pretty far away. So we need to consider that data can be the data model should be probably revised and adopted for that particular system we are moving to. Synchronization, use only when necessary, because synchronization slows you down, and therefore pick up the toolkit which suits your needs. So revisit your requirements and see what amount of synchronization you really need. Thread per partition can improve simple operations, but also can slow down a little bit complex ones. So we need to be aware of that and just see what can be done in this or that case. Okay, here is my email. I also invite everyone to participate in our open source community. So come and join us and help us to develop Apache Ignite. Participate in our dev lists and user lists. So thank you very much. Questions? Yeah, you're welcome. You want a mic? Is it correct you're doing like safe pairs or something like that? So I actually I understand what the question is that when we are saving like some Spark data set to Ignite, the locality cannot be preserved, and Ignite data is distributed in different way. So the simplest probably and very straightforward solution, I would just generate the key for Ignite that will stay on that particular server, because I doubt if you do like ordinary cache get operations. So you probably load the data and do some SQL processing or some scanning of the data set. So I would just generate the key and make sure it comes to local node. No, no, I didn't say that. I said that I would play as a very straightforward solution. I would play with the key generation and to generate a key that stays locally. But so I think that your question is a good candidate to be sent to user list. So if you haven't done so, please do it. You can send the email right now, and you will probably get a response overnight. No, but okay. So you're right that Ignite node need to start and need to connect to the cluster. This is like a complex procedure because we need to know that all that mappings and that topology, all nodes in topology. So you'd probably be good if you start Ignite node once and then just use it.
Yeah, the things that we're trying to share the Ignite connection across multiple Spark jobs
Mhm.
because each Spark job is like a Java process. Runs in one JVM. If we have different Spark jobs, we have different JVM, right? If each Spark job start to run, start the Ignite connection, and after the job finish, then shut down the Ignite connection. Then another Spark job run, start the Ignite connection again.
No, but you're probably
So if we can share across multiple jobs,
no, you cannot share data between processes without like out of the box. I don't know such techniques. Uh, Probably better solution would be supporting some lightweight protocol, which we are working on now. So you will be able to connect to the cluster with a thin client, and therefore thin client does not require complex starting procedure. It's very lightweight. It just opens the socket and that's it, and start working immediately. So probably you need to try this out. In any case, uh, can you please send your question to? There was not questions regarding the talk, but there were questions regarding Ignite. So. And all the questions regarding Ignite, please send to user list. This is the proper place for that questions to be asked. Okay, welcome.
About distribution for the IoT slash time series application. So you want some locality because like you want to do range queries like time slices, but you do want to distribute them across the cluster to prevent hot spots. Any suggestion how you do it? There's some principles with respect.
No, but actually, when we insert that type of data which is monotonously growing, it always a pain in any systems because it like causes the contention in certain index pages and but for now I would think if I would see if we can split the ranges, let's say the first half of a second on this server, a group of servers, second half of a second on this, like an idea.
But that will generate like hotspot kind of
Wow.
all the sensors, right?
No, but if we well, every put to cache will generate some something. So you affect the system. Systems like does what you want, and it involves some friction, of course.
I think question is, do you have some recommendation how to do time series processing?
Uh,
How to store time series data, how process it?
I think that short answer is no. So we don't have a documentation unit for this, but I think that if you so ask this question on the user list, so we will think about that. For now, I've even so I can't answer this in general, but so I would play with some distribution. So I would, let's say, put some dates here, some dates here. Then for the range, I would calculate the nodes I need to go to cover all that range, and something like that. And this will make this will reduce the contention, by the way, because I know exactly that this key should go here, and another key goes there. Therefore, contention would be reduced if compared to the case when both of the keys goes to the same node. Okay. Any more questions?
What about service grid? Sounds like from your presentations could create an extra latency in the system. And in outside, it's recommended to use on the like Apache Ignite website, and we are moving to our service grid. But if it's data and services kind of separated, sounds like it's going to be another layer of latency.
But okay, I don't get the question. So
But data node service nodes.
okay.
This is when you deploy
Mm.
grid as separate,
Mhm.
but data nodes and service nodes separate.
No, but you still, so there is no magic. So if even if you remove your service and just access your data from another machine, this will introduce latency already. So if service is deployed separately, you think of it as of accessing data remotely. So you probably, if it is really a problem, then you would probably try to deploy your servers on your data nodes. Yes, you're welcome.
Yes. So you talked about assigning partitions to nodes, and I was curious: is it possible to migrate a partition to another node dynamically?
Yes, the short answer is yes, and that's what probably be very easy to do. So you just implement the affinity function interface, which basically has only, let's say, only two important methods, which is partition. You map key to partition, and then you assign the partition set to nodes. So this way, I think that Sberbank has their affinity function, so they have some configuration file for that affinity function, and I'm pretty sure if we need to migrate the partition, we can do it with their mechanisms. So Ignite already supports it. So when new node comes to topology or leaves the topology event is fired through all the cluster, and then nodes will start exchanging with the partition maps. It just maps the information about the partition location in the cluster. And after this process is finished, the rebalancing starts. And rebalancing goes in the way affinity function is assigned on this particular topology version. So I can do it like mix everything on each topology version, but that would probably not the best affinity function in the world.
Okay, but in theory, like if you have a number of transactions on a particular partition and you want to send it over to a node that has like more CPU allocated to it or something, you can do that. It's possible.
Currently we don't have API for this. So you will need to fire, let's say, the minor topology changing event. So this can be done artificially, I think, through public API, and then your affinity function should support it. So you need to send signal to your affinity function. You say, hey, there will be a topology event shortly. Let's move this and this in this way. So you drag it from UI or you change some config file. I don't know.
Okay.
So this is your implementation detail, but it's still possible, I think.
All right, sweet. Thanks.
Thank you. Okay, no more questions. So you can find me on the booth or on Apache Ignite website. Thank you.